Hello, in this video, we want to take a look at using the integral test. So remember, the integral test is that if the function is continuous, positive, and decreasing, then we can look at the integral. If the integral converges, so does the series. If the integral diverges, so does the series. We're going to take a look at our first example. The example is the series k equals 1 to infinity of k e to the negative k squared. So we identify that our function is the function x e to the negative x squared. Take our sequence and turn it into the function. And we want to know, is f of x continuous for x greater than or equal to 1? Or maybe some other number if it's not from one non. But is it continuous? Is f of x positive for x greater than or equal to 1? And is f of x decreasing? The first two questions are pretty easy to answer. So first, the question of continuous. For the question of continuous, we're looking at the function f of x equals x e to the negative x squared. This is also x over e to the x squared. E to the x squared never equals 0. Does not matter what x is put in, that is never 0. So, yes, since our denominator is never 0, f of x is continuous. Is it positive? Well, for x greater than or equal to 1, the numerator is positive because it's just x. X being greater than or equal to 1 means that x is positive. And e to the x squared, that's an exponential that is never negative. So the numerator is positive, the denominator is positive, positive divided by positive, it's positive. So those two questions, easy to answer. Decreasing, we need the first derivative test. So we're going to use the first derivative test, which says if the derivative is negative, then the function is decreasing. So f of x equals x e to the negative x squared, meaning f prime of x equals, by the product rule, e to the negative x squared plus x e to the negative x squared times negative 2x, which is also 1 minus 2x squared, all times e to the negative x squared. Where f prime of x equals 0 is when 1 minus 2x squared e to the negative x squared equals 0. We already said e to the negative x squared is never 0. Let me set that up here. So we're just looking at 1 minus 2x squared equals 0, which is when x is plus or minus the square root of 1/2. That is our critical point. So setting up a chart, we know that it's possible for this first derivative to switch between positive and negative at negative square root 1/2 and positive square root 1/2. What I want to note, though, is we only care about x greater than or equal to 1. And 1 is bigger than the square root of 1/2. What that tells us is when we're checking this first derivative, we don't care if our function is positive or negative, or increasing or decreasing from for any x less than negative square root 1/2. We don't care. Between negative square root 1/2 to square root 1/2, we still don't care. We only care from this 1/2 onward because we care about 1 onward. So if x equals 1, just a test point inside of our interval, happens to be our starting point, but I'm picking a test point inside the interval we worry about, then f prime of 1 is equal to negative e to the negative 1. If you plug in 1 to our first derivative. Negative e to the negative 1, or negative 1 over e, is negative. So here our function is negative from square root 1/2 onward. So yes, f prime of x is less than 0 for x greater than or equal to 1. So f of x is decreasing for x greater than or equal to 1. So all 3 properties are met. Great. Going back to our test, we have all 3 properties. So now what we want to do is look at the integral. If the integral converges, then so does the series. If the integral diverges, then so does the series. So because we have these 3 properties met, we can look at the integral from 1 to infinity of x e to the negative x squared dx. And this is an improper integral. We need a limit. So that integral is equal to the limit as t goes to infinity of the integral from 1 to t of x e to the negative x squared dx. This is a u sub problem where u equals negative x squared, du equals negative 2x dx. So we still have that limit as t goes to infinity of negative 1/2 the integral from plugging in our lower and upper bounds, negative 1 to negative t squared of e to the u du. The integral of e to the u is e to the u. This is the limit as t goes to infinity of negative 1/2 e to the u evaluated from negative 1 to negative t squared. Plugging in that upper and lower bound, we have negative t squared plugged in minus e to the negative 1 And the limit as t goes to infinity of e to the negative t squared is 0, because that would be the limit as t goes to infinity of 1 over e to the t squared. That denominator will just be growing exponentially. That limit goes to 0. Meaning we have negative 1/2 times negative e to the negative 1, which is 1 over 2e. What this means is the integral 1 to infinity x e to the negative x squared dx converges to 1 over 2e. Now, by the integral test, because the integral converges, so does the series. So because the integral 1 to infinity x e to the negative x squared dx converges, so does the series. The series n equals, or k was our variable, k equals 1 to infinity k e to the negative k squared also converges by the integral test. So remember those sentences we were talking about, or I mentioned in previous videos? The series converges or diverges by test because reason? The series converges by the integral test because the integral converges. There are all the properties for our complete sentence of justification. So zooming out to see all of this problem. For integral test, we need to check the 3 conditions, make sure those 3 conditions are met before looking at the integral. Then, if the integral converges, so does the series. If the series diverges, then we would see that because the integral diverged. So if the integral diverges, so does the series. We'll take a look at another example in the next video.